Well, after we talked about the angular momentum, the rate of change of angular momentum, that is the torque experienced by a group of particles. Now, we have to find the angular momentum of a group of particles. Angular momentum of a particle about an inertial reference point is given as r cross mv. If there are so many particles, we can calculate the angular momentum of all particles individually and add them up to get the net angular momentum. And we want to derive the expression for net angular momentum of a group of particles about a point, inertial reference point, and to categorize that angular momentum into two parts. One will be the angular momentum of the center of mass with respect to the reference point. Other will be the angular momentum of the system of particles measured with respect to center of mass. Let us proceed there. Suppose it is a system of n number of particles. Particle 1 moves with velocity v1. It has mass m1. You take the reference point O. This is the position vector of the particle 1 with respect to this reference point. You can take the position of the second particle, that is R2. Its mass is m2, that its velocity v2. Angular momentum of the first particle with respect to the reference point is L1 is equal to R1 cross m1 v1. Angular momentum of the second particle with respect to the reference point is L2 is equal to R2 cross m2 v2. In this way, you take ith particle, its mass is mi, and this position vector is ri. Let it move with velocity vi. This is the ith particle. Its angular momentum with respect to the given reference point O is Li. In this way, the nth particle, which moves with the velocity Vn and having the position vector Rn, can be given as, its angular momentum can be given as Rn cross Mn to Vn. We have to add all the angular momenta of all particles with respect to this reference point. The individual angular momentum of the particles are then the net angular momentum of the system of particles about the reference inertial reference point O, whose velocity is 0, let, for the sake of simplicity, this is the stationary point We can assume for the sake of simplicity. Well, if you sum all the angular momenta, then the net angular momentum can be written as L is equal to L1 plus L2 plus Li plus Ln. Or in a nutshell, we can write Li sum means addition of all the angular momenta. I ranges from 1 to n. The system of n particles. Li is equal to Ri cross MIVI. And the net angular momentum is L is equal to sum of angular momentum of all particles. Li is equal to Ri cross MIVI. I is equal to 1 to I is equal to n. In this system of particle, for the sake of clarity, let us take ith particle. Its mass be mi, its velocity is vi, position vector is Ri with respect to the given reference point. Let the center of mass of the system of particle be C, and its position vector is Rc, and ith particle's position vector with respect to the center of mass is Ric. The position vector of ith particle, that is Ri, can be written as Ric plus Rc, Rc plus Ric is equal to Ri. Galilean transformation of position, Ri can be written as Ric plus Rc. The velocity of ith particle, that is Vi, can be given as Vic plus Vc. According to Galilean transformation, of displacement and velocity. Now substitute these two parameters in this expression to get Ric plus Rc cross Mi Vic plus Vc. Summation of this. I is equal to 1 to I is equal to n. First term multiplied with the entire. So you can just write I is equal to 1 to I equal to n summation Ric cross Mi Vic plus Ric cross Mi Vc plus. Now this is multiplied with the whole term Rc cross Mi Vic plus Rc cross Mi Vc. So we are getting 4 terms. Let us glorify each term. This term can be written as Ric cross Mi VIC summum from I is equal to 1 to I is equal to n plus first term is the second term summation I is equal to 1 to I is equal to n, or I say cross MI VC. Let us go to third term. Sum n is equal to 1 to n is equal to I is equal to 1 to I is equal to n, or say cross MI VIC plus sum I is equal to 1 to I is equal to n, or say cross MI VC. Fourth term. Let us glorify the first term. Or I say cross MI into VIC. This is the momentum of ith particle, linear momentum of ith particle, and this is the position vector of ith particle with respect to the center mass. Since the position vector cross the momentum, position vector with respect to center of mass cross the momentum of the particle, ith particle with respect to center of mass, we can call it angular momentum of ith particle with respect to center of mass and addition of all. So this first term gives us the total angular momentum, a total angular momentum of the system measured with respect to center of mass frame. I can call it, let RIC cross MIVIC I is equal to 1 to I is equal to n with the angular momentum of the system measured with respect to center of mass. Let it be L dash. Or you can write LC. Now come to the second part, second term. Let us take the second term. Or I say cross MIVC. This term can be written as, since this is a scalar quantity, mass, you can put it MIRIC cross VC. I is equal to 1 to I is equal to n. This is a constant quantity for all the points because this is the velocity of center of mass. Therefore, we can just write this factor and bring it out of this factor. And this quantity is the sum of the first momenta, the first momenta of the mass, the sum of first momenta of all the particles measured with respect to the center of mass. We know that M1 R1 plus M2 R2 in this way if you go on adding up to Mn Rn by total mass of the system as Rc, as per the definition of the center of mass position. If you take these position vectors with respect to center of mass, R1c, R2c, Rnc, this will be RCC. Sum of position vectors, sum of the masses, or the sum of the product of masses and the position vectors of the particles with respect to the center of mass, or we can call sum of first momenta of mass is equal to 0 because RCC is equal to 0. Position vector of center of mass with respect to center of mass is always 0. Therefore, Mi RIC sum of all from I equal 1 to I equal to n is always equal to 0. This term will be equal to 0. When this term will be 0, the entire term will vanish. The second term will be equal to 0. Since the second term will be equal to 0, if you differentiate it, you are getting sum of I is equal to 1 to I is equal to n, or you can just write the same thing, but take the derivative. This will also will be equal to 0. This will also will be equal to 0, but this is equal to the velocity of ith particle with respect to the center of mass. I is equal to 1 to I is equal to n is equal to 0. This physically signifies sum of the first momenta of the masses is 0 because position vector of the center of mass with respect to itself is always 0. Let us come to this term. Since RCC is 0, when this will be 0, this will be 0. But this term is none other than the sum of the first momenta of all masses. Symbolically, we can write summation I is equal to 1 to I is equal to n, MIRIC will be equal to 0. So the second term will be equal to 0. Now come to the third term. The third term, we have assumed the angular momentum of the system measured with respect to center of mass, which is given by the first term, let it be LS or LC. The second term will vanish. The third term is RC cross MI VIC. Sum of this term I is equal to n to I is equal to 1, I is equal to 1 to I is equal to n. This is the momentum of the ith particle with respect to center of mass. This is a constant quantity because for all the particles RC remains fixed. It is the position vector of the center of mass with respect to this point. So therefore, we cannot take it as a variable. Therefore, we can take it out of the summation cross MIVIC. I is equal to 1 to I is equal to n. This is the sum of momenta. Which momenta? Linear momenta of all particles with respect to center of mass is always equal to 0 because this is 0 already we proved with respect to center of mass. Therefore, if you take the derivative of both sides, obviously this will be equal to 0. But this is nothing but the velocity of ith particle with respect to center of mass. Summation of this will be always equal to 0. In this way you can prove, or let us come to this shows that the sum of linear momenta of all particles with respect to center of mass is always 0. There is another method also. Since velocity of center of mass with respect to ground is given as sum of momenta of all particles with respect to ground or any fixed reference point upon the total mass of the system. If you take the reference point fixed to the center of mass, this will be the velocity of the particles with respect to center of mass, or this will be the momentum of ith particle with respect to center of mass prime, or the entire numerator term will be equal to the sum of momenta of all particles with respect to center of mass of the system. Therefore, the left hand side will be equal to, instead of ground, this will be center of mass prime. Since velocity of center of mass with respect to center of mass is 0, we can say that velocity of ith particle with respect to center of mass into mass of ith particle, the momentum of ith particle and sum of momenta of all particles is equal to 0. So this is another way we can conclude that the vector sum of momenta of all particles of a system of particles measured with respect to the center of mass frame is always equal to 0. So the third term, RC cross MIVIC sum. You can take it out of the summation sign. RC cross MIVIC. This is the summation of momenta of all particles with respect to center of mass of the system is 0. Since this will be 0, the entire term will vanish. The entire term vanishes. The third term therefore will vanish. Now come to the fourth term. The fourth term of the expression of the angular momentum of the system of particle with respect to the fixed reference point is RC cross MIVC, sum of this. These two are constant quantities. Therefore, we can just write RC cross, take the sum symbol of the summation to this point, and since Vc is constant, you can put it out of the symbol, out of the bracket. This signifies the total mass. So RC cross total mass of the system Vc. So this physically signifies that the entire system's mass is located here as capital M, and this signifies that center mass velocity. The total mass supposed to be centered at this point into the center mass velocity can be called momentum of center of mass, and that also can be written as momentum, linear momentum of the system of particles, and summation sign we need not put, because already you have put the summation and you obtain the total mass of the system as capital M. So the fourth term signifies RC cross MVC. This is the center of mass point. Entire mass of the system is imagined to be centered at this point. The center mass velocity, and we can call it momentum of the center of mass. Linear momentum is multiplied with this. So RC cross MVC can be called angular momentum of the center of mass. So this term can be called angular momentum of the center of mass with respect to the reference point O. So this can be written as RC cross MVC. Capital M is the total mass of the system. Therefore, we are left behind with two terms. This is LC, the angular momentum of the system of particle measured with respect to the center of mass, and this is the angular momentum of the center of mass measured with respect to the given reference point. Hence, the angular momentum of the system with respect to O is given as angular momentum of the system measured with respect to the center of mass frame plus angular momentum of the center of mass with respect to the given point. The angular momentum of the system with respect to O is given by this expression. This states that the angular momentum of the system about any reference point O, say. This may be fixed or it may be moving with certain velocity, doesn't matter. The angular momentum of the system about any reference point, this is LO, is equal to angular momentum of the system with respect to center of mass plus angular momentum of the system or of the center of mass with respect to the given reference point O. In words you can write like that, and as a formula mathematically we can state in this way. So angular momentum of the entire system with respect to this given reference point is equal to angular momentum of the same system measured with respect to the center of mass frame plus the angular momentum of the center of mass measured with respect to the given reference point. This is one of the great theory of the system of particles. The first term, LC, can also be called the spin angular momentum. Or intrinsic angular momentum. This signifies the rotation of a system of particles. If LC is not equal to 0, the system is said to be rotating. सिस्टम में be rigid, the system may be rigid body or it may be non-rigid, like liquid or gases. It may be solid. And the second term is called angular momentum of the center of mass or orbital angular momentum. Orbital angular momentum. This is just the angular momentum of the center of mass point with respect to the given reference point. So, in rotational mechanics, we will be dealing with this factor, spin angular momentum. This is an intrinsic property of the medium, of the system, internal property of the system. This also can be called internal angular momentum. This is the property of a system, and this is, it is a property. Which property? Internal property of the system. Suppose if you take a bucket of water and just put your hand and rule it, the water will rotate. It is because the angular momentum of the water entire or sum of angular momentum of all particles with respect to the center of mass of water is not equal to 0. And we can say that even though water is not a rigid object, the water is rotating. Whirl pull, the air rotates, causing the whirlpool, the eddies, which physically signifies that the angular momentum of all the air particles measured with respect to the center of mass point or the axis passing through the center of mass is not equal to 0. Therefore, we can say that the air is said to be rotating. So, angular momentum of the system of particle is the sum of two angular momenta. One angular momentum of the system of particle measured with respect to the center of mass frame, and the angular momentum of the system measured with respect to center of mass. This is the total mass of the system. This is the internal angular momentum, and you can call it external also, or angular momentum of the center of mass, or we can call it angular momentum spin, and we can call it angular momentum orbital. Because of the orbiting motion of the center of mass, this angular momentum is generated, and because of the spin of the system, the angular momentum LC is generated. That is the sum of angular momentum of all particles measured with respect to the center of mass. If it is non-zero, then the system is said to be rotating. Let us take a few examples to clarify this theoretical derivation. Well, let us take this example of two particles connected by a rigid massless rod. Rigid massless rod of length L, suppose this moves with velocity v. This Rod rotates with an angular velocity omega. Find the angular momentum of the system. This is the entire system. With respect to O, this is the center of mass. The O is at a distance of L from the layer mass. Of the system, with respect to O, of the system, with respect to C, LO is equal to LC plus RC cross MVC. Now LC is equal to, with respect to the center of mass, its velocity is equal to L by 2 into omega, its velocity is equal to L by 2 into omega. Therefore, with respect to center of mass, its angular momentum of this particle 1, angular momentum of the particle 2 with respect to center of mass. If you add, you are getting the total angular momentum of the system with respect to center of mass. So L1C is equal to L by 2 into omega into MVR, MV into R is equal to L by 2. Which direction? Minus k cap. And this is also having same angular momentum with respect to center of mass. ML by 2, M into L by 2 into its velocity, that is L by 2 into omega MVR, and the angle between these two is 90 degrees. Therefore, the sin theta is 1. And this is also pointing in minus k cap. So, ml square omega by 2 minus k cap. Answer, that is LC. With respect to O, this is R1. R1 cross M1 V1 plus R2 cross M2 V2. R1 is equal to L plus L2L J cap cross M1 equal to M, and its velocity, that is V1, is equal to V1C plus Vc. Velocity of 1 with respect to C is equal to L by 2 into omega I cap, and Vc is equal to Vi cap. So L by 2 omega plus V, using the kinematical ideas of rigid body. So V1 you write L by 2 omega plus Vi cap plus, for the second particle, this is the position vector with respect to this point R2. What is R2? Lj cap cross velocity of 2 as equal to velocity of 2 with respect to center of mass plus velocity of center of mass. The center of mass moves with velocity v, therefore Vc is equal to Vi cap. And with respect to center of mass, the second particle moves back, therefore its velocity is equal to L by 2 into omega in negative I direction. Velocity of the second particle is equal to V minus L by 2 omega. into M. I, J, K. J cap cross I cap. J cap cross I cap equal to minus K cap, or anti-clockwise direction, because R cross V, R cross V1 is clockwise to M, L, L omega by 2 into V minus K cap. J cross I, J cross I is equal to minus K cap, minus ML V minus L by 2 omega K cap minus K cap. So you can take common, minus ML K cap, you take common, this is L omega plus 2V. Plus V minus L omega by 2. So L omega minus L omega by 2 will be equal to L omega by 2. Just simplifying the factors, we can get minus ML K cap, L omega minus L omega by 2 equal to L omega by 2 plus 2V plus V will be equal to 3V. Answer. If you need to calculate the angular momentum of the center of mass with respect to the given point RC cross MVC, that also you can calculate. RC is equal to center of mass is here, and this position vector is equal to L plus L by 2, that is 3L by 2 in J cap direction. RC 3 by 2 L J cap plus cross. Total mass of the system is M plus M, 2M, and center of mass velocity is given as V I cap, and RC cross VC is in, or J cap cross I cap is minus K cap, same thing. 2 will getting cancelled, 3 M L V minus K cap, and you can verify that when you are adding this factor with the factor LC, you will get this value. You calculated LC as angular momentum of the system with respect to the center of mass as M L by 2 omega into L by 2 into 2 minus K cap. That's equal to ML square by 4 or ML square by 2 into omega minus K cap. So let us verify. Add this to LC plus RC cross MVC will be equal to, what is LC? Minus 3 ML V K cap, and RC cross MVC will be equal to minus 3M L V K cap, and LC will be equal to minus ML square by 2 omega K cap. If you just add this 2, you are getting minus ML K cap 3 V plus L omega by 2. What we have got is the angular momentum of the entire system with respect to the given point, and that is equal to LO. Hence verified. So angular momentum of the entire system with respect to any reference point is equal to angular momentum of the entire system with respect to the center of mass plus angular momentum of the center of mass with respect to the given reference point.